Okay, so the first thing we're going to do is talk about factoring. Now, factoring, you need to understand it is exactly backwards of the multiplication that we had done right before. So the first thing of factoring, we're going to have 5 methods up here, and this kind of covers all of factoring. So make sure you're familiar with these 5. This is how the teachers are teaching it. So first thing, you're going to pull out the greatest common factor. Best way to teach this one is that it's exactly opposite of the distributive property. For example, you have 2x goes into 5x squared plus 3x minus 7. That's 10x cubed plus 6x squared minus 14x. When you erase that part, you look at this problem right down here and you say, all right, somebody jumped something through. What was it? What do you got that goes into 10, 6, and 14? They're like, it's a 2. And it looks like there's an x there. And then they pull it out. That's the way we can do greatest common factor. Now, this actually leads to the next one by a good casual process. When you have 2xm plus 5m, and you factor it, they can easily identify it as somebody jumped an m in there. Pull out the greatest common factor, and you have the 2x plus 5. 2xh plus 5h. If you set this up correctly, they'll look at that and they'll be like, oh, some students will get it, some students won't. If they need a little bit of help, go a little bit weird with them a little bit. 2x mat plus 5 mat. You're like, okay, what was jumped in? Well, mat was. (2x squiggle plus 5 squiggle). Well, that's going to be, well, the squiggle jumped in 2x plus 5. So when they see you get, they should be able to pull that t plus 3 right out, and they get that. Now, in particular, this is where they should start seeing their answers look like problems that they had done previously. And that's really important for them to see that. So you can go 2x, put an x in there. And they should be able to do that. Not too bad. So we have the very, okay, so this leads us to the next one. If you write this out, they will think, that nothing's jumped in. Tell them just take the first 2 and the second 2, see what they come up with. What can you pull out of this one? You can pull a 2 and an x out of that guy, and you get that. And you're like, oh. Pull a 5 out of that, and you're right up here, and then you can do it. And this is called grouping. Specifically, if something has 4 terms, they're going to expect you to group. And that's exactly what it is. These 4 terms are exactly the F, the O, the I, and the L from FOIL. So the O and the I, when you do the first 2, you'll get something that comes out of them. The last 2, something comes out of them. And that's why the 4 terms are able to be factored by grouping. So this kind of, that will help them with the first couple. So the third one, I call this one trinomial fast. Other people write it like this. In particular, this deals with ones that they're able to do mostly in their head. And I start off with, so x plus 3x plus 5. And they multiply it out. Sometimes it'll take them a while to get refreshed on, okay, I'm going to take the x into the x, I'll do the x squared, and then they'll say, okay, that's plus 5x plus 3x plus 15. You do it a couple of times. Oops. You do it a couple of times. X plus 7, x plus 2. Pretty soon, somebody is going to start getting the idea, hey, wait a minute. Do you think it'd be x squared plus 9x plus 14? Yeah, they're starting to see the pattern. They add to this, they times to this. So, once they get really good at that, just ask them. So, what about x squared plus 11x plus 30? Say, what did I start with? And they should be able to say, okay, there had to be an x there to get that. Okay, we have to have a 30, so something times something is 30 that adds to 11. And it's nice. That's what I call trinomial fast. If you have an x squared without any coefficient in front of it, you're able to do that. Now this one, number 4. Slow or long or whatever. They'll write it like this: ax squared plus bx plus c, where a does not equal 1. Students don't appreciate this until they understand the concept. But this is the idea. They will practice grouping quite a bit. They like this one. They can break it up into pieces and they love it. So when they get something such as this, they look at it and what times together is 6 adds to 13. They're like, nothing. But it still works. I tell them, you know that 13x in the middle? It came from somewhere. In particular, that particular 13 came from a 9 and a 4. That was the O and the I term that added together to that. Say, okay, how many terms does it have? And they'll say, well, it's got 4 terms. Say, group it. Let's see what happens. And so, like, okay, we have a 3x coming out of there. We have a 2 coming out of there. Oh my word, look at that. There it is. Pull out the 2x plus 3, have a 3x plus 2. About that time, students will say, yeah, okay, that's fine, but where did you get the 9 and the 4 from? Don't tell them yet. It's best if they really, really want to know where that 9 and 4 came from. So you do another problem. In particular, let's do a whole nother one here. Okay, so when you do it again, 9x squared minus 16x minus 4. Say, that negative 16, I'm going to tell you where it came from. It came from a positive 2x and a negative 18x. You're like, okay, can you do it from there? And most of the time, they will say, yep, I can do it from there. But where did you get the plus 2 and negative 18? How do you know it's not a negative 20 and a positive 4? How do you know it's not a negative 3 and negative 13? Let them try some of those numbers and see that factoring won't work. There's only that one set that'll work. And then you do it like this, and it's like you're holding some grand secret that they really want to know. Pull out the 9x plus 2. There you have it. And so they'll be dying to know. And you say, well, let's try, would it work if there was a KO? What if it was a plus 9? Could we do that one? And they'll take guesses. Let them guess. It's a great thing for them to just think about. For them to, but where did they get those numbers from? Then the rest of it is easy once they get those numbers. So then you can say, okay, I'll let you know how I did it. 9 times negative 4 is negative 36. And I looked for numbers that times together to give you negative 36. So let's look at all those. 1 and 36. 2 and 18. You see, like, that's where I got the 2 and the 18 from. 3 and 12. 4 and 9. 6 and 6. One of them has to be negative. That's how I know those are the numbers. It must times to that. You've got to include the 9 and the negative 4. Remember this right over here with trinomial fast, these are easy. It's when you put a number out in front that messes it up. So that's why we have to take this 9 times the negative 4 before we use that number, because this number is the one that's making us not be able to do it fast. So, negative 3x plus 12x, and those are the middle terms where you're able to group. Take out the minus 3. And you're doing grouping. And they feel really good up to this point. So this is really the key, and that's why this is often called the AC method, is because you're taking A times C, and then you split the middle. Okay? Then, the fifth one. Special cases. Two terms. This is where you have the difference of squares. Or the sum difference of cubes. So, with that in mind, these are the 5 methods, and you should be able to test your students and say, okay, this polynomial has 3 terms. What are we going to use? Well, one of those two. Has 4 terms. We're going to do that. This one, everything can have a greatest common factor pulled out of it. It has 2 terms. Well, is it a difference of squares? Is it a sum or difference of cubes? Can we pull those out? So with that, there's a flowchart that I've kind of made up. Actually, one of my 100B classes made it up because they were like, okay, so when we have it, how can we tell? I would not suggest teaching this flowchart at the very beginning. It's not going to work very well. But once they've practiced these a lot, there's always a section in the book that says, okay, let's throw them all together and see if you can determine which polynomials you're going to use this on, which one's going to be here, which one's going to be there. And they also have, I ought to write this down, perfect squares. So, this flowchart should be in your mind, and if they really want to know, say, okay, when we get one, let's go through and help them make this flowchart. So, I'm going to make it over here. We'll see if we can do it. So, first thing, step number 1. If you come up on a polynomial, first thing you do, no matter what, pull out the greatest common factor. That's the first thing. Then you go to the next step, which is, you ask the question, how many terms does it have? Because that's what really differentiates these things. If it has 2 terms, could have 3 terms, could have 4 terms. If it has 2 terms, you're either a difference of squares, or you are a sum or difference of cubes. Math 100B students don't need to worry about this right here. So you'll just say, it's going to be a difference of squares. So, and then you're done. If it has 3 terms, the question really is, what does A equal? Well, no, we've got to do something before that, don't we? We have to do just check it, see if it's a perfect square. Those look like 25x squared plus 70x plus 49. Particularly, you're looking at those 2 numbers. Are they perfect squares? So check it. If it's yes, fine. If not, you move on. You say, You move on and you say a equals what? If a equals 1, then you're going to do a fast one. If a does not equal 1, then you're going to, let me see if I can draw this. You're going to take a times c, and then you're going to split the middle. And from there, you now have 4 terms. So you're going to do grouping, which, if you have 4 terms, is exactly like that. Now, that looks really complicated, which is why you would not want to give it to the student immediately. But eventually, they should be able to produce that because they've learned it. When they just look at these and you just give them a polynomial and say, okay, what are we going to do first? And they'll say, it's got 3 terms, let's do this one. Nope, got to do the GCF first. Then you just got 3 terms, let's do one of these 2. Well, what's the difference? This really is when a equals 1, and this is when a does not equal 1. And so they're really going through that and say, okay, let's draw this out. Let's see if we can make it. That's not essential for the students, but some will really appreciate it. And they're like, wow, it's like a machine. You drop the polynomial in here, and you're done. By the time you either hit this edge, that edge, or that edge. And so you're able to do it. So that should be the summary of most factoring that you'll be able to do. Factoring has certain uses. When we did fractions early on, we told prime factorization was the way that you could take a number, split it up, dissect it, look under the microscope, see what it's really made of. Well, factoring does that for polynomials. That's exactly what it is. It's prime factorization for a number that we don't even know what is. That's what it. So when we have something like 21 over 49. Now officially, when you're reducing this, you're like, oh, 7 goes into both of those, you cross them out and you get 3/7. Well, this would be akin to having, I don't want that one. Let's try that again. This would be akin to having that problem. Now, the students will see this fraction, see that, and say, oh yeah, I can take a 35 and a 21. Easy, I can cancel those. You need to remind them that over here, they couldn't cancel the 2 and the 4 because this bar is a division sign. It only undoes multiplication. So here, this is a subtraction sign. You can't take a divide sign and undo a subtraction sign. You have to turn this into things multiplying together. That's the idea of factoring. So we take this up here, x minus 7, x plus 5, x minus 7, x plus 3. Notice that this is very similar to us writing this. 7 times 3, 7 times 7. That's the official way simplification happens. Same thing over here. So the rules for polynomial fractions, also known as rational expressions, is the exact same process as what they did with fractions. Anytime they are misunderstanding that, this is a great thing to go back and say, wait, this is exactly what we were doing. Same thing. When we were adding fractions, you had, say something like 2/10. We better put something else there. 3/10 plus 4/15. Now, some of them are able to get a common denominator just by looking, so you might have to make more difficult problems. However, for those that can't, this is a 2 times a 5. This is 3 times 5. You remember how to do a least common multiple? You have 2 times 5, well, least common multiple, least common denominator would be a 2 times a 3 times a 5. That goes in there, that goes in there. So you say, we need to times this by 3, times this by 3, times this by 2, times this by 2. So we have 9 plus 8. And then the end fraction, we have 17 over 2 times 3 is 6, times 5 is 30. So it ends up being 17/30ths. We cover that way back in arithmetic, but they've probably forgotten this process of specifically using this factorization to get the least common denominator. So when you have a fraction such as that plus over that problem, it turns out that this process is crucial, because to find the least common denominator of those two quadratic polynomials becomes very difficult. So you're going to do the same thing. Factoring, like those 5 things we went through, become the foundation of everything that is beyond them. So in this case, this factors into x plus 7, x minus 2, and that's what we're doing. We're just doing this to the number. This over here, x plus 2, x minus 2. So the least common denominator, we need to make sure this is there. We need to make sure that one is in there. The x minus 2 is already there, so we have an x plus 2. To make this a common denominator, we need put an x plus 2 on there, just like we did with the 3 over here. For this one, we need an x plus 7. That's the complexifying of those fractions. So we have 5x plus 10 plus 3x plus 21. So overall, we get 8x plus 31 over that denominator. Same exact process. Same thing with multiplying them together. Same thing with rational equations. There are always going to be the exact same steps of what you did in fractions with the prime factorization as what you do with rational expressions, rational equations, complex rational functions. It's going to follow the exact same process. Students have a hard time making that leap. So being able to connect it will really help them. Okay, the next thing, when we deal with radicals, there are a couple of patterns that evolve when we're multiplying binomials that come in really handy, such as multiply those two together. Oh, look, there's no middle term. It's like magic. It happens every time. Try another one. Try another one. And x squared minus 25. Some students right now will think that all of a sudden we're not doing FOIL anymore. Make sure they understand that we really did x times negative 5, positive 5 times x, and that those two canceled out. It was a special thing, and these partners that go together have special names. It's not an opposite. It's called a conjugate. When you get to this point, it will help them understand when you have to rationalize a denominator, such as 2 over the square root of 7. We're trying to times by something on top and bottom that will get rid of the square root. It's easy to see. Have a square root of 7 on top and bottom. The top has a square root, then square root of 7 times square root of 7. They may need some help with that. To understand exactly that square root of 7 times square root of 7, they may, oh, that's the square root of 49. You're like, which is like 7. Do a couple of problems. We take these two times together. See if you always get that number. Square root of 9 times square root of 9, does it equal 9? Square root of 10 times square root of 10, does it really equal square root of 10? I mean 10 all the time? And it does. So that's the idea. So when you give them something like this, 3 plus square root of 5, they're going to look at that and they're going to think, let's times by the square root of 5. Don't get after them for it. That's the natural thing. That's what you've just trained them to do, is to see the square root times by the square root of 5. However, if you do that, you guys know what happens. It is not so nice. You get 2 square roots of 5 over, that jumps in, you get 3 square roots of 5 plus 5. We still have a square root on the bottom. We did not fix our problem. That's when these patterns come in really handy. Particularly if you say, okay, what's 3 plus the square root of 5 times 3 minus the square root of 5? 9 minus 3 square roots of 5 plus 3 square roots of 5 minus square root of 5 times square root of 5, 5. Those are gone. 9 minus 5 is 4. This miracle that occurs by conjugates happens with radicals. Adding them, subtracting them, just like terms. But when you're multiplying them, if you ever do conjugates, you end up with something that has no square roots in it at all, because it squares the beginning and it squares the end. So in this case, once they try that, you're like, okay, so we have to times this so there are no square roots that end up anywhere, and that's the setup for it. So we get 2 times 3 minus the square root of 5 over 3 times 3 is 9. Middle terms cancel, minus 5. They will debate on whether or not that 2 can cancel with that 4, because the 3 wouldn't be able to because it's next to a minus sign, but the 2 is next to a times, which is opposite of divide, so that is what can cancel. So the answer then, 2 over this is 3 minus the square root of 5 over 2, and there's no square root in the bottom. So when you're rationalizing, that's pretty nice. That provides a really good foundation for imaginary numbers. I squared negative 1, and that's what the definition is. We made that up. There is no number in the world that multiplies by itself to give you negative 1. All the positive numbers times by themselves give you something positive. All the negative numbers times by themselves give you something negative, give you something positive. 0 gives you 0. So every number that we know of times by itself will give you something positive or 0. There's not a number out there that gives you a negative 1. So we made him up. So anytime you see an I squared, just turn him to a negative 1. Otherwise, it acts like a variable. I cubed. Some of them will have a difficult time saying, okay, my teacher told me that I cubed was the same as negative I. Why? I write it out like this. These two right there make a negative 1. Negative 1 times I, that's where the negative I comes from. You got I to the 4th. There's a negative 1. There's a negative 1. It's 1. And then you keep writing it down. They start seeing this pattern emerge. Then just for fun, say, okay, what do you think I, and give them an easy one to begin with, I to the 488th power is? And we're like, I have no idea. Like, which one do you think it lands on? Well, we got 4 of them. That's going to be 1. It's going to be 1. How many groups do we have? And they'll see, aha, let's take 4 into that. So we have 122 of these guys. So 122 times, all boils down to 1. You're like, okay, so what would I to the 489th be? And they'll be able to do that. They'll pick up the idea of remainder. You take this, divide it by 4, see what the remainder is. You will either have 0, 1, 2, or 3. It'll go in even, or you'll have that remainder, and so they only have to know 4 of them. They love that as a shortcut. I only have to know 4 of them, that's it. And really, they only need to know 1 of them. And then you get the other guys from that. They're usually pretty good about multiplication, where anytime they get an I squared, it's just 1. But they don't like the division. So if you have like 2 plus 3i over 5 minus 8i. They don't like that. And they're like, I don't know how to divide. Tell them, yeah, that's right. We don't really know how to divide, but we do need to get all radicals off the bottom. They will have done some with rationalization of denominators. If this were a square root of -1, how do we get square roots off the bottom? It's right back to this thing again. And you're using that word again. This is in 3 separate places. You have it with binomials when you're timesing them together. You have it with radicals when you're timesing them together and you want to get rid of the square roots. Let's try it with this. When we come back here and we're multiplying imaginary numbers, we're going to use the exact same thing we just did, where we're going to times by the conjugate. 5 plus 8i and 5 plus 8i. Now, on the bottom here, we have 5 times 5, 25. 5 times positive 8i is positive 40i. 5 times negative 8i, negative 40i. They're gone. That's exactly what happens. So we have a negative 8 times a positive 8i, and we get negative 64i squared. I squared is what? Positive 1. So 25 plus 64, and so we get 89 as the denominator. So on top here, we're going to have 10 plus 16i plus 15i plus 24i squared. Now again, the I squared is a -1. So we have 10 minus 24 is a -14. 16 and 15i, you have a plus 33i. Now, if you write this in standard form, you get -14 over 89 plus 33 over 89i. And these 3 methods are quite, well, they're the foundation of everything you do in 110 with the polynomials, everything you're going to do in calculus whenever you have to factor and solve polynomials. We need to be able to solve quadratics. We can get our handle on every single quadratic answer. We get i's, we get square roots, but we're completely covered with square roots. Cube roots, huge, big, ugly formula. Fourth roots, we can't, there is no formula that we can actually create. Well, it's really nasty. There's sort of one out there. Fifth, just so you know, the 5th polynomial and higher does not have one. You actually cannot create a formula with square roots, addition, subtraction, 5th roots, 18th roots, whatever, and combine it and get a solid answer for any of them. So, the fact that we can do it with squares, we exploit that all the time. We'll always break stuff down into quadratics because we can solve it. And there are 3 major types that we need to do. So first we got the factoring. Now this isn't just the process of factoring, this is a method of solving a quadratic equation. We have the factoring, completing the square. And then we have the formula. Now for you as tutors, you may recall when you were taught these 3 that when you did factoring, you're like, oh yeah, factor and set equal to 0 and set each factor equal to 0, that's fine. Completing the square, you probably skipped. You probably like saw that a couple of times and you're like, oh yeah, that's back in the back somewhere. And you're like, well, the formula takes care of everything, so why do we even need to do it? Then you got up to the point where you studied circles and ellipses. And you probably struggled. Hyperbolas, stuff like that. That's because completing the square was not firmly grounded. If you're tutoring a student that is going into the sciences and needs to know how to do hyperbolas and ellipses and all those conic sections, circles, you're going to need to know completing the square really well. And it's not that bad once you go behind the scenes and look at what it is. But let's make sure we understand the factoring. If we have something like 5x squared plus 8x minus 4 equals 0. When I'm teaching this, you can teach them and just tell them the process. We'll factor it and set each equal to 0. But I find it a lot nicer if you start off with something like this. 3x equals 0. You say solve it. They're like 0. Big question of the day. Where did the 3 go? Did it just vanish? Did you just like took a hike? Where'd it go? Some people say, well, officially what we did, we divided by 3, but 0 over 3 is 0. Okay, good. Whatever it did, should note 0 is the only thing that can work there. Take a step up after a few of those problems. Can I do the same thing and write this? Now, mostly, students will want to distribute, get rid of the parentheses. 3x minus 15 equals 0. But ask them, is this true? Can that 3 go the same place that 3 did? Like, well, yeah. Look how easy it is. 3 times something is 0. That something has to be 0. That is a number in and of itself. 3 times something is 0. Well, then it's x equals 5. It's kind of nice. Now, give them this kind of problem. Better stick with 2 separate variables. It'll be nice. Actually, do this one first. Say, okay, t can take a hike just like the 3 did, and you get y equals 0. Y can take a hike just like the 3 did, and you get t equals 0. You get 2 separate answers. You've got 2 different variables in there, I can get 2 separate answers. So then you get down to this and say, okay, this guy can take a hike, because if this times is, it doesn't matter what this is. If this guy's 0, it makes the whole thing. So if x is 7, that'll work. If t is negative 3, that'll work. Then you can start to have some fun. So you give them something like that. Say, okay, can you list off any answers? And they should realize at this point that there is one number that is so important to this being able to be solved, and it's this guy right here. Everybody knows there's 0 times tables because they're so easy. 5 times 0 is 0, 8 times 0 is 0, 10 times 0 is 0. So anything times 0 is 0. That's the key. So we have all these numbers. If we make x equals 0, 0 times anything is 0. There's our one answer. See if we can pick out some nice easy ones. If x equals a negative 2, negative 2 plus 2 is 0. That number is a 0. The whole thing, we have a solution. They will like this. That is an ugly problem. Doesn't matter what country you're from, that just looks terrible. Piece at a time, x equals 7, x equals 2. Those are the easy ones. Now, when you get some of the harder ones, say, okay, let's try it. Let's make this guy right there equal 0. People spit out like, oh, negative 5 or something like that. Not quite. So you get a fraction on this guy, but test it. See if it works. If you stick that up in there, 3 times negative 5 thirds, it's going to be negative 5 plus 5 is 0. It actually multiplies by anything. Just go ahead and stick negative 3 5 thirds anywhere else, and you get 0. And so then you're able to do that. So once they get this down, and you do a couple of examples like that, kind of close to the original problem they asked, but not too close. Write down something like, no, gotta have a 2 there. Just write down that one and see if they can solve it. And they'll be like, well, yeah, sure, I can solve that. After what we just went through, this is a piece of cake. Look, x is negative 2, and some will do it in their head, but some will have to look at it. 2/5. Like, huh. Tell them to ignore the 0 and factor this guy. You may have to go back through those 5 methods. Can you pull out a greatest common factor? No. How many terms? 3. What's the leading coefficient? 5. It's not equal to 1, so we have to do 5 times negative 4 is a negative 20. Look at the, split the middle. So we have a 1 and a 20, a 2 and a 10, 4 and a 5. That's all we got. What adds up to positive 8? It looks like a negative 2 and a positive 10. We now have 4 terms. Factor. Take out a positive 2. got -2 and a +10. Oh, sorry, I missed that 5. There we go. So we have a 5x minus 2. Take the 5x minus 2. Oh, look at what we have. You're like, what's interesting is you take these 2 points right here, well, these 2 numbers, stick them back up in here. Actually run it through a couple of times. 5, and you get 0 both times. That's a good time to bring out. There are actually 2 answers to that problem that make it work. So that's how you introduce by factoring. Once they're in factors, we get this powerful property of the number 0. So you first, like if they need to write it out, you first get it equal to 0. 2 factor. You have 5 methods to help you with that. It's a good place to bring that up. And 3, set each factor equal to 0. That's how you solve by factoring. Now, completing the square. This is best introduced by what I consider these 2 good examples. X squared equals 9, x squared equals 7. Over here, x squared equals 9, you can follow these without any problem. Okay, let's pull the 9 over here. Factor, it's a difference of squares. That's method 5, 2 special cases, 2 terms. So you get x equals a -3, x equals a +3. Now, if you try the same thing over here, you're going to be stuck. There are no numbers that times together to give you 7 that are going to be conjugates like that. So you're like, okay, now wait. We have this idea of peeling off stuff in algebra. You've got this artichoke or onion or whatever you want to call it. So you want to peel this stuff off. Well, what is the opposite of squaring something? You're going to square root it. So let's try this one. If you just square root to do like this, you get x equals 3. Notice that you did not get both of the answers. That is the motivation right there. That just square rooting only gives you a positive, where indeed there are 2 numbers that when you square them, they give you 9. They cut off the negative one for you tutors. They did that specifically to make square root a function. It was not defined as a function until they said, let's pick one of them. So, anytime you square root, you need a +3 and a -3. That allows you to do this. X equals plus or minus square root of 7. And it works. It's a little bit unusual for them. They're like, oh, I've never had a square root as an answer. And you need to be empathetic. They haven't. They now know how to deal with square roots, but they've never had an equation that looks perfectly fine up here, looks very similar, but has an answer that's completely, radically different, pardon the pun. So, with this principle here, we build up the following. X plus 2 squared equals 7. Now we could come over here and, expand it out, then get it equal to 0, then factor it, and then try to set each factor to 0. But what if it doesn't factor? What if we're going to end up with not nice answers? They're going to have square roots. Factoring doesn't work for those guys. So, right here, do the peeling off, the artichoke. Don't forget the plus or minus right there. You actually have 2 equations right now. You have x plus 2 equals negative square root of 7, and you have a plus. If they need to separate that, let them do that. That's all right. Otherwise, they can see them both together. Subtract 2, subtract 2. Do another one. X minus 4 squared equals 19. 319. The beauty of completing the square is that you can deal with numbers however large you want. When you square root, you don't have to worry about this factoring thing where you've got to know, okay, what numbers times together and add together. That's not as essential, especially when you're doing a square root. So you have x minus 4 equals plus or minus make sure we get that in there. Square root of 319. X equals 4 plus or minus square root of 319. Those are the answers. And you can test them. Tell them to put it in their calculator, put it in here, and see what happens. Well, when you subtract the 4 is gone. So you get square root of 319 squared, 319. If you set that up well enough, then give them just a little taste of this. Some outlandish number over there that you know this is not going to come out to be a good, nice number. They can't factor it. Be like, okay, so how are we going to solve this thing? This is a good time to introduce the perfect squares. They have seen it once before, but they haven't been able to apply it. They don't know how to use it yet. So in particular, do this. Say, what is that squared? We'll be like, they may have to do the, until they get this. You say, okay, x plus 3 squared. A little bit quicker. X minus 7 squared. After a while, they start to see a pattern. You're like, see if you can do this without doing it the long way. This is really good to see that these two are exactly the same. Say, okay, I'm going to make one over here. You tell me what I'm making. X squared minus 12x. Say, what would have to go right over here for there to be a perfect square? Like, which one of these am I making? They're like, well, it's obvious. 7 is half of 14, 9 is half of 18, 3 is half of 6. So you're making x minus 6 squared. Like, okay, so what number has to go right over there? If you were to times that out, you get x minus, well, it's a 36 you have to add. Excellent. Make them do that about 4 times. You say, that red box, you have just put something onto a polynomial and created a perfect square. You've completed it so that it now is, you can write it like this or like this. So you say, okay, what about this one? X squared plus 25x. They'll say, well, you're making x plus 5 squared. You're like, yes, I am. So what do you have to add on? A 25. Good. So you're saying I could rewrite this as that. That is when they start to be like, whoa, these are easy. You're going to square root and subtract 5. They're like, whoa, that's an easy problem, because it would not have been able to be possible under factoring anytime you have a radical in the answer. So that's how we set up the need for completing the square. So then we give them stuff like this. X squared plus 10x plus 2 equals 0. That's not so nice. It's not a perfect square. That 2 is the wrong number. We can't write it as a square root of 25. This is where they should be encouraged to think they have complete power. They have total authority to do anything they want as long as they do it to both sides. Subtract 2 from both sides. Okay, what number has to go there so we're in this list? Like, well, you're making x plus 5 squared. You know by that number. And that's where we start getting the process. You're going to take 1/2 of that number, goes right there. But you need something else before it's exactly the same, and that's when you square it. You can't just add 25. You've got to do it to both sides of the equation. And that becomes the whole process for completing the square. So equals 23, and then you can, by the time they get to that point, get down here, they can almost just write out the answer. Now, they need practice with that before putting a number in front here. They really need, they need the whole homework assignment. So before they're even introduced to the formula. So in particular, what I'm about to show you, this should help you in your, not just for the students, but this should help you with your dealing in calculus with parabolas, circles, hyperbolas, and ellipses. Any of those conic sections. This is the process and the concept behind it for which you're going to be able to turn any hyperbolas, whatever, into standard form, because everything's written in a perfect square. So, eventually, they need to get to be able to do this problem. Okay, the first issue is we cannot, even if we subtract 7 over here, you'll notice in this list, everything is a 1. That's a 5. Bad news. We got to get rid of that. They know how to do that. Now, they have fractions. I understand that many people are scared of them, but if the answer is going to end up being fraction and radical, you've got to deal with it. So, now, they've done a lot of those, so let's follow the process. We're going to try to make x plus 11/10 squared. We have to make sure they understand how to half a fraction. 1/2 of 11/5. You go back, the word of means times. 11/10 is half of 11/5 equals, well, let's find out what number we've got over here. We had to add 121 over 100. So, common denominator. That's what? 1900ths? Negative 1900ths. So now when we square root both sides, plus or minus, we have x equals 11/10 plus or minus this I square root of 19 over square root of 100 is 10, common denominator. Plus or minus I square root of 19 all over 10. Those are the answers. They don't look nice, but that's completing the square at the very possible worst it can be. Now the formula came around. Now pay attention, you guys are going to be expected in the packet to derive the quadratic formula. This is how you do it. So I'm going to do it here. You may need to replay it 3 or 4 times. I do it probably 4 or 5 times in my class so that they understand that it's this process that gives us that formula. So that's completing the square. I'm not going to write down steps for that because it's more of a concept. Somebody was doing the completing the square a whole bunch and decided, okay, since I keep doing the same process over and over and over again, there seems to be a pattern going on. Let's see if I can do it with a random A, B, and C, see what the answer pops out to be. So, they subtract the C over, divide by A. We're trying to make, well, we're going to take half of that. Remember, you've got to have done fractions for this to make sense. That's a B over 2A. 1/2 of that you times top and bottom. So we need to make sure and add this squared. Now that's a perfect square and we can write it like that. Over here, common denominators 4a squared. We have to times by 4a, times by 4a, so it's a 4a squared and a 4a squared. And you start to see the formula form. And square root both sides, plus or minus, and we get x plus b over 2a equals plus or minus the square root of b squared minus a 4ac all over. Square root of 4 is 2, square root of a squared is a. Now technically, for those of you that are really picky, square root of a squared is absolute value of a. But with the plus and the minus up here, it automatically takes care of that a could be positive, could be negative. We don't know. So we now Subtract that over, and we have a common denominator, and we get x equals negative b plus or minus square root b squared minus 4ac all over 2a. Now, that formula in itself is kind of lyrical, kind of like a little song. There are a couple of songs to that they will be taught. There are actually two. One of them is a nice little Pop Goes the Weasel tune, and the other one is a rap. I will not do the rap for you, but I am going to do this song for you. Okay, so follow along, pay attention to it. We have x equals negative b plus or minus square root b squared minus 4ac all over 2a. That's the song. They will be taught that, and in fact, they've been known to whistle during the exams. It's not cheating, so unless it's too loud, then it's bad. But if they need to memorize it with a song, that's really nice. And of course, you know the value of the formula is that now when you take any nasty, bad, awful problem like the one we had a 5x squared plus 11x plus 7 equals 0. Now, note that it has to be equal to 0 for this to be useful. We know that the answer is going to be x equals, so negative b. I think I put a negative there, didn't I? So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Should be 11 plus or minus the square root of negative 19. Oh look, square root of negative is I all over 10. And I think that's what we had before, or something similar. Okay, the final part of this is when we are going to graph parabolas. This is the last part of 101. It'd be nice to go into the circles and hyperbolas and stuff like that, but we don't have room for it in Math 101 currently. So in graphing the parabolas, usually there are 4 things that they need to be able to do. They need to be able to label intercepts, and they need to be able to graph the vertex, now, I said 4 things. How many intercepts are there going to be in parabolas? If you look at what they look like. So we've got to find those 3 points and that one, and the vertex. Okay, intercepts. X-intercept happens. Should harken back to what they learned about lines. X-intercept happens anytime y is 0. Y-intercept happens anytime x is 0. And then the vertex we'll get to in a minute, but I want to go over these really quick. So y-intercept first. Give an example. We have y equals 3x squared plus 13x plus 4. Ooh, I don't like that one. Go minus 13x plus 4. Okay, so get the y-intercept. This is the easiest one they should be able to do. You stick in x is 0. Stick in 0 everywhere in x is. 0, 0, 4. They will remember y equals mx plus b. That b is still right out there. We have a lot more with the x now, but that b is going to be right there. Okay, so that gives us one of the points. X-intercept happens when y is 0. So we're going to write this equation out. Good time to ask how many answers you're going to have. They'll probably respond 2 after they've done several of these. They're like, oh, we get plus or minus this, or that 2 has been brought up quite a bit now, and that was what was so surprising. They'll get 2 answers, and that's correct. 2 points for x will get y to be 0. So we have 3 methods of solving this thing now. We can factor, we can complete the square, or we can use the formula. They'll probably want to go to the formula, bunch of wimps. This is a really good problem because if they do the formula, it actually requires a lot more work. In this case, if you look at it, we have 3 terms. Take out the greatest common factor, no dice. Leading coefficients of 3. 3 times 4 is 12. Oh, 1 and 12, look at that. They're both negative. If they're both negative, we have negative 13. So we get a negative x and a negative 12x. So we get, taking x out of that guy, 3x minus 1, and looks like a negative 4 out of that one, and we get 3x minus 1. Good. So 3x minus 1, x minus 4. And yes, they have to go through and solve this. This used to be the whole problem. It is now only half of the problem that they are dealing with. So we get x equals 1/3 and x equals 4. That means 4 will give them 0 and 1/3 will give them 0. Now the vertex. Let's put this right here. The vertex is right in the middle. Now in reality, even with the formulas that they give you in the book, this is really how the vertex is found. It is right in the middle. We now have 2 points, one at 4 and one at 1/3. What's right in the middle of those two? So you take 4 plus 1/3, that's going to give you 13/3, divided by 2 is 13/6. That's not a nice number for them to deal with. Oh well, they're in a math class. 13/6, you stick it in. You want to find out what y value comes out of there. So you take 13/6, square it, 169, yeah, that's right, 169, 36, 12 minus 13 times 13 over 6, plus 4. Put that in your calculator and you get the other thing right there. Now, after you do a few of these problems, especially one that needs the quadratic formula, there's something that comes out. I find this is a really nice way to introduce that little negative b over 2a thing. If I have something like this, I say, okay, 3x squared plus 5, there's going to be no factoring going on. In fact, we're going to be up there, and we're not even going to have x-intercepts. They're going to be imaginary. When they use the formula, x equals negative b plus or minus square root b squared minus 4ac all over 2a. When they use that, you've got negative 7 plus or minus square root 49 minus, what is that, 2060? So negative 11 all over, is that right? 49, okay, negative 11 all over 6. A really neat experience for them to do is to take two separate numbers of this form at all, like 2 plus the square root of 5 over 7, 2 minus the square root of 5 over 7. Any two numbers that are conjugates like that, and have them average the conjugates just on their calculator. These two average to 2/7. These two numbers, they're imaginary. You've got a negative under the square root here. They're imaginary. These two are going to average to negative 7/6. That thing where the vertex is negative b over 2a, and then you stick it in to see what the other guy is, didn't just fall out of heaven. This is where it came from. You've got the formula, if you recall. This number, when you take these two separate numbers, they'll be the x-intercepts right there. When you average them, you get negative b over 2a. That's the middle line. And that's why you're able to say, oh yeah, negative 7, 6 is where the vertex is going to be.